Good morning, everyone. My name is Thomas Zhang, and today I will be presenting my final project for CS 5300 computer vision. The title is Handwritten Text Recognition on IAM, the core IAM database. IAM is a public database for OCR handwriting problem. The core question I'm going to investigate is if you fix architecture and focus entirely on the data, the quality, the composition, and the decoding strategy, how much can you actually move the needles? Let me start with the problem. Handwritten text recognition is a task of automatically transcribing a line image like this into digital text. The standard benchmark for English handwritten is IAM handwriting database, about 13,000 line image from 657 different writers. IAM is generally treated as a gold standard. The assumption is that the annotation are essentially correct, around 95% or higher accuracy. But here's the thing, if you look at the handwritten cursive, you immediately see why this is hard. Taking the letter pair O and A, they share the same oval stroke, or N and M, which different only in stroke count, or R and S, where a subtle loop make all the difference. These ambiguity are real and they affect human annotators. And as I will show you, they affect automate system in exactly the same way. So the framing of this project is deliberately data centric. I'm holding the model architecture fixed, a standard CRNN CTC, and asking for specific questions about the data pipeline. The first question is, does the systematic hyperparameter search substantially improve the baseline? The question second is, can a vision, language, model audit and clean IAM annotations, and does prompt design matters? Question three is, does the targeted system synthetic data augmentation improve rare character recognition? And in question four, does a three-level decoding pipeline grid, then beam search with a language model, and then spelling correction provide meaningful and addictive gains? Each of these correspond to one contribution to this project. The architecture, before getting into experiments, here is the system. The architecture is a standard CRNN CTC pipeline. A 7-layer VGG CNN extracts a special feature from the input image. A 2-layer bidirectional GRU encodes the sequence, and the CTC decoder produces the character transcript. Total parameter count is about 16.7 million. Input height is fixed as 64 pixels. Width is a variable, and the vocabulary covers 80 characters, letters, digitals, punctuations, plus a CDC plan token. I want to emphasize, this is not a competitive architecture. TR-OCR, transform-based OCR, and other transform-based models perform better. The point of using CRN and CDC is experimental control. I want to isolate the effect of data decision, not architectural ones. Experimental theory design. To answer the 4 research questions, I designed 5 experimental series. Experiment first is baseline, the full IM training set, which has 6,482 samples, no synthetic data. Experiment 2 use aggressively VLM cleaned data. I will explain that shortly. The experiment 3 is primarily the augmentation experiment, the full IM plus the synthetic data at scale from times 1 to times 10. Experiment 4 combines aggressively cleaned set with the same synthetic pipelines, and experiment 5 does the same with a conservative clean set. Each theory is designed to answer a specific sub-question, and I'll walk you through them in order. First is hyperparameter search. Let's start with question 1, hyperparameter search. I run 14 configurations in parallel and across the 7 GPUs using a greedy sequential search. Change one thing at a time. Keep it if validation CER improves by more than 0.05%. You can see the result here. The blue bars are configurations that were kept. Gray ones were discarded. And the gold bar is the best result. The 2 biggest gain were expanding the bidirectional GRU hidden sets from 256 to 512, which alone cut validation CER from 9% 0.04 to 7% 0.35, a drop of 1.69 percentage point, and then increasing the learning rate from increasing the learning rate from 1 e increasing the learning rate brought it down from 6.29. The takeaway that bidirectional GRU was a bottleneck, not the CNN. Once we gave the sequential encoding enough capacity, everything else fell into place. The optimal configuration, bidirectional GRU hidden size 512, dropout 0.03, batch size 32 is what I use for all subsequent experiments. That is a 30% relative improve over all the vanilla baseline, and we haven't touched the data yet. And VLM annotation auditing. Now, question 2 is the most surprising result in the project. I use TikTok Double Seed 2.0 Pro and to audit all the 10,000 IM examples, every training, validation, and test line. The VLM is given the image and the claimed annotation and asked to judge whether they match. I tested the two prompts. The V1 prompt was aggressive. It told the model to arrow on the slide or flagging. Vision 2 was conservative. It told the model to default to correct and explicitly list common files, positive traps. Digit zero versus letter O, British spelling abbreviations. The results are stark. V1 flagged 33% of the training data and removes 2,144 samples. When I retrained on that very clean set, test CER went from 8.43 to 10.33. It got worse. V2 flagged only 12%, removed 814 examples, and produced essentially no change in CER. Why did aggressive cleaning backfire? Two reasons. First, removing a third of your training data costs under fitting. Second, and more importantly, many of the sample V1 flagged were not actually error. They were hard examples. Cases where O generally looks like A, where N generally looks like M. The VRM is as confused by these as human annotators would be, which bring me to the cross matrix finding, and this is something I generally proud of. I built two confusion matrix. One is from the VLM audit, which character pairs did the VLM most often flags as errors, and one from the model prediction on the test set, which characters pairs does the trained model mostly often confused. If this reflected independently system-specific bias, we had expect them to be uncorrelated, but if they both reflect the genuine vision ambiguity in cursive handwritten, it should be correlated. The Spearsman rank correlation across the 65 shared substitution pair is 0.6, with p less than 0.0001. That is strong significant correlation. And when I break it down by visual categories, the pattern is even cleaner. And when I break down by visual categories, the round and oval characters pairs like O, A, E, C, G, Q, the correlation is 0.942. For stroke and accent pairs, N, M, R, S, it's 0.65. For cross categories pairs, it drops to 0.354. This gradient directly mirror the visual structure of the cursive script. Oval characters share the most stroke level feature, so both the VRM and the model find them maximally confusable for the same understanding physical reason. The practical implication, VRM confusion pattern, especially for round oval pairs, can serve as a high confidence prior to targeted data collection or confusion guide post correction, and that's exactly how I use in the decoding pipeline. So question 3 about synthetic data augmentation. The IM training set has a character frequency imbalance of 24,000 to 1. Common letters like E and T appears tens of thousands of times. Rare characters like hash symbol appears fewer than 10 times. My pipeline addresses this directly. I built a text pool of about 28,000 sentences. IM labels doubled for in distribution vocabulary. LM generated sentences that are dense in rare target characters and rule-based templates for digits and punctuations. Font rendering uses the TRDG library with 14 fonts. There are 9 handwriting styles, 5 print plus random skew, blur and distortion, and the resulting pool is 65,000 synthetic samples stored in LMDB format. You can see from the frequency chart that the synthetic distribution is much more balanced. Rare characters that were nearly absent in IM now have meaningful representations. Augmentation result of synthetic data helps. Here are the results across the 3 augmentation theories plotted as a test CER versus a synthetic scale. You can see the this on this line. We can see the greedy line, but different levels of scales of synthetic data. Here are the results across all 3 augmentation theories. Experiment 3, full IM plus synthetic improves monotonic from 8.48 at 0 scale to 7.53 at 10 times. That is 11% relative improvement. And here is a per character breakdown confirmed that the synthetic works where it aims. The largest gain concentrated in the rare characters in my pipeline, especially targeted hash symbol CER drops from 100% to 60%. Semicolon drops from 41.7 to 21.7. Question 4, pipeline of architecture and the design of decoding pipeline. After training CTC greedy decoding gives us a character level argmax at each frame. It is fast, but has no concept of word. Common mistake like recognizing think as think ending with K as ending with think ending with U are left uncorrected because the decoder treats every frame independently. Step 2 is beam search combined with Ken language model program. I trained the model on 103,000 sentences. I am labeled plus 20 Project Gutenberg novels with 73,540 words mixed case vocabularies. The beam search reweighted hypothesis using word level n-gram probability, which immediately handled out of vocabulary sounding sequence. Step 3 is confusion guide spell correction. Any word that is out of vocabulary after beam decoding is a correction candidate. I apply single character substitution drawn from the model's own confusion matrix, the same one we discussed earlier, and correct if the result is a valid vocabulary. One detail that turned out to be important, the vocabulary must preserve case. When I use a lowercase only vocabulary, proper nouns like London and Manchester were penalized as unknown. Switching to mixed case save 0.23% on its own. The pipeline results that consistent and addictive across all experiment theories. For our best setup, experiment 3 with 10 skills synthesized data. Greedy gives 7.59%, Beam plus Kern language model bring to 6.28%, a drop of 1.33% point, and spell correction add another 0.26, reaching 5.94%. The 1.33 from beam rescoring is larger than the 0.94 from 10 times synthetic augmentation. It requires no retrain whatsoever. One particularly striking result is experiment 3 with a full decoding pipeline achieves 6.1 with 0.16 percentage point of the 10 scale result at 5.94%, while using 1/10 of the synthetic data. The implication is clear. Invest your decoding pipeline before invest your decoding pipeline, or invest on the language model before you scale your data. The marginal value of language model rescoring is higher than the margin value of the synthetic volume, especially once you have a reasonable greedy baseline. Here's the SOTA comparison. For context, here is where our best results sit relatively to the state of art. Our 5.94 is competitive with the best CRN CTC result in the literature. The previous CRN CTC state of art achieved 5.14, but that one used a residue shortcut architecture, especially designed for handwriting. We are within 0.8 percentage point of that using standard CRN with data-centered improvement. The gap to TRLCR and DRAT HTR around 3% point is expected and intentional. Those models are hundreds of millions of pre-trained parameters pre-trained on other data. Our contribution isn't to beat them, it's to show how much pure data-centered work data-centered and language model analysis can accomplish within a controlled architecture setting. And here is the analysis of cost benefit. If I have to summarize the cost benefit picture in one sentence, the Kern language model beam rescoring gave the biggest CER gain, requiring no retraining and cost almost nothing to run. Synthetic data require GPU time and careful scale management. Spell correction is essentially free. The best strategy is get your language model pipeline work first, and then add synthetic data to push your greedy baseline lower, which in turn gives the language model more work with. Conclusion, let me answer the full research question directly. First one, yes, hyperparameter search gave a 30% relative gain. Hidden size matters most. Question 2, it depends entirely on prompt design. Aggressive, clean hurts. The cross matrix correlation tell us why. The confusions are genuine visual ambiguity, not annotation error. And question 3, yes, with caveat, augmentation works. I mean, data synthetic works, but require a real data anchor of at least 5,000 samples. Below that threshold, you get anchor effect. Question 4, yes, the best result is 5.94%. Language model rescoring outperform 10 scales synthetic data augmentation at a fraction of the cost. The broader takeaway, data quality, data composition, and decoding strategies deserve as much engineering attention as architecture search. Thank you. I'm happy. Thank you. That's all for today.